What is the Joule-Thomson effect? The Joule-Thomson effect can be defined as the phenomenon of temperature change produced when a gas is allowed to expand adiabatically from a region of high pressure to a region of extremely low pressure.
Joule-Thomson effect occurs when a gas or liquid is forced through a valve or stopper. It will experience Joule-Thomson effect, which causes it to rapidly expand. The closed system's potential and kinetic energy change as a result of this quick expansion. Joule-Thomson cooling effect can cause changes to the thermal potential and kinetic energy. Any increase in potential energy will result to a drop in temperature and kinetic energy in a closed system. Temperature is defined as the measurement of thermal kinetic energy. The system experiences adiabatic expansion, which heat does not leave or enter the system.
How does Joule-Thomson effect happen? By undergoing throttling, where throttling is the process of limiting fluid flow by just partially closing the valve, a gas experiences a reduction in pressure, which, under certain conditions, leads to a decrease in temperature. This phenomenon, known as the Joule-Thomson effect, involves a temperature change in the gas. When the process occurs within specific temperature and pressure ranges that ensure a positive effect, where the gas temperature decreases as pressure is reduced, throttling can effectively cool the gas and facilitate its liquefaction. The following conditions must be met. Firstly, the gases must have extremely low saturation temperatures and pressures. Secondly, to achieve a state with a positive Joule-Thomson effect, the gas must first be pre-cooled using auxiliary classical refrigeration systems. Lastly, achieving very low temperatures requires substantial pressure drops. For example, in the case of hydrogen, the pressure before throttling must be 110 bars, and the gas needs to be pre-cooled below 190 K, approximately 83 Fahrenheit, to achieve a positive Joule-Thomson effect. Firstly, there would be no change in enthalpy. The determination of whether the internal energy increases or decreases takes place by whether work is done by the liquid or on the fluid. Secondly, the Joule-Thomson coefficient makes possible the quantification of the temperature change during a Joule-Thomson expansion display. Lastly, this coefficient may be either positive or negative. It is negative at extremely high and extremely low temperatures. Furthermore, it is negative at very high pressure at all temperatures. We can conclude that being positive corresponds to cooling, while being negative corresponds to heating.
Can we apply it? Yes! For the application in industry, we use Linde's method, also known as the Linde process. Linde's method is a technique used for the liquefaction of gases, particularly air, and for the industrial production of liquefied gases like oxygen, nitrogen, and argon. This method leverages the Joule-Thomson effect, where a gas cools on expansion when it is below its inversion temperature. The process was developed by Carl von Linde in the late 19th century. First step is the compression. The Carl surface a gas first compressed to a high pressure, about 200 atm, using a compressor by reducing its volume. This increases the temperature of the gas due to the work done on it. Next, pre-cooling. The high-pressure gas is then cooled to room temperature or below by passing it through a heat exchanger. Air leaving the compressor is cooled by cooling water, where cooling water is pumped and sprayed over the hot air, and the cool air then flows through the condenser. It is then passed through a spiral pipe, having a jet at the end. Through the jet, the gas expands out into a region of low temperature. Moreover, throttlings, Joule-Thomson expansion, cooled high-pressure gas is then allowed to expand through a throttling valve, which causes it to cool further due to the Joule-Thomson effect. The lower the temperature of the air entering the throttle valve, the greater the fraction of air that is liquefied. Expansion is adiabatic, meaning no heat is exchanged with the surroundings. Furthermore, recursory, the heat exchange and recycling. The two-phase mixture of air enters the separator, from where liquid air is withdrawn and liquefied air is recycled. Lastly, liquefaction, as the gas is repeatedly cycled through the process, it reaches temperatures where it starts to liquefy. For air, this involves primarily liquefying nitrogen and oxygen.
Industrial processes that involve the liquefaction of gases, such as the production of liquid nitrogen, oxygen, or natural gas, rely heavily on the Joule-Thomson effect. By carefully controlling the expansion of these gases, they can be cooled to their liquefaction points. In conclusion, the Joule-Thomson effect is a cornerstone of modern thermodynamics, with widespread applications in various industries. It exemplifies how theoretical principles can be applied to solve practical engineering challenges, thereby enhancing technological development and efficiency in industrial processes.
Please scan the QR code for the references list. Thank you.